Good morning, everyone. I'd like to start by inviting Wilfred Kendall, as President of the Bernoulli Society, to make an announcement.
Thank you very much, Christina. The Derblad Prize has been established by the Bernoulli Society, acting through the Committee for Conferences and Stochastic Processes, which oversees this series of conferences, and it's very generously funded by Springer. It's awarded every 2 years for excellent work in probability, carried out by someone in the first part of their career. And it gives me very great pleasure to announce that the 2014 award is to Gregory Miremont of Lyon.
So I'm delighted to introduce the first speaker of today, Christophe Garban, also from Lyon. Christophe has made several very important and beautiful contributions in various areas of probability and statistical mechanics, including noise sensitivity, percolation, the Ising model, SLE, and Liouville quantum gravity. And today he's going to speak to us about near-critical percolation and the minimum spanning tree.
Thank you very much for this invitation. I'm very happy to be here. In this talk I will tell you about a joint project that we started quite a long time ago with Gabor Peter, with here this week, and Odette Schramm. And we only finished this project last year. So I will start as a warm-up with the following well-known problem that you probably all heard about, the traveling salesman problem. So imagine you want to visit all these highlight points in Buenos Aires. To avoid confusion, north is of course pointing southeast, as in all the maps. And you have just 1 day, so you want to visit this, and you want to minimize the cycle that spans all these points. So if I give them a mess it up, it would be a solution like that. So among all the cycles, you want the one of minimal length, and this is known as the traveling salesman problem. And what we will be interested in this talk is to try to look at objects like that, seen from very far away, to try to have scaling limits of objects like that. So here is a picture of the United States with the vertices are all the cities that have more than 500 inhabitants. And if you want to visit them all, it will take you quite a lot of time. But the optimal path is supposed to look like that. So we don't see it very well. You can think of it as a kind of random piano curve in the plane. The randomness comes from the position of the cities of more than 500 inhabitants. And in this simulation, which is not mine, they had the nice idea to color in blue the interior of this piano curve, and it looks like that. And I like this picture very much because the randomness is complicated. You have states with a lot of cities and states like Oregon with very few. Nevertheless, one starts seeing a kind of a limiting object that arises, namely the shape of the curve in very dense regions is similar to what one sees in regions that are less dense. And it's reasonable to conjecture that as the number of points tend to infinity, one should have a unique limiting object for the problem of the traveling salesman problem. So I am not going to prove a theorem like that for this problem, because as is well known, the traveling salesman problem is an NP-complete problem in combinatorics. So that makes it very hard to study large-scale geometry and things like that. So instead of looking at the shortest cycle, we will consider another model in combinatorics that is very well known too, and which is not NP-complete, which is the model of the minimal spanning tree. So now, instead of looking at the cycle, I will try to look among all the combinatorial spanning trees that span these cities. I will seek for the one that has minimal Euclidean length, and maybe it will look like that. So I have finitely many spanning trees that have straight edges, and I take the one whose sum along all its edges is of minimal Euclidean length. And this will be what I call a minimal spanning tree. I did not find a minimal spanning tree on the example I had before, unfortunately. But here is how a minimal spanning tree would look if you take a large number of random points in a unit square. And the question we are asking in this talk is there a scaling limit as the number of points diverge to infinity? And we will have an answer. We will build a tree, which will be a dense tree and which should be the scaling limit of this Euclidean model. And we will prove that this indeed is the scaling limit of the spanning tree on the graph. So let me define the model on the graph. So if one takes D2, now the randomness that I will use is that I will put random weights on edges. For example, I can take a uniform random variable independent on each edges, but it could be some other distribution than the uniform one. It's not very important, it's a set. And now that I have my random weights, so the randomness previously was the location of the cities, the location of the points. Now the randomness arises from these random weights on edges. And now among all the spanning trees of this graph, so trees that are embedded in this graph and visit all vertices, I want to take the one of minimal total weights, and almost surely there is a unique one, and it would look like that. And the question in this graph setting is there a scaling limit as the size of this D2 box goes to infinity? So here is a picture that was made by Oded Schramm. It's a minimal spanning tree in an n by n box. And what he did is he has chosen 3 vertices, generic vertices in this box, and has drawn how the paths from these 3 vertices look. And one sees that one can see that as n goes to infinity, it's reasonable to guess that these paths will be fractal type of curves. And the question is there a scaling limit of this whole object as n goes to infinity? So, in this conference, we've seen many contexts where scaling limits are important. We've seen this in the KPZ setting. We've seen this also in random planar graphs converge to the Brownian map, a bit in Scott's talk, and we've seen many settings where we have discrete objects, discrete random object, and we want to seek for its scaling limit. And I want to give you 2 other settings where one has nice results in this direction. And this first result is very related to the talk I'm giving, because it's also about spanning trees. But now the randomness behind is different. The randomness I'm interested in this talk is this minimal spanning tree where we fixed the random weights. But you could do something different. You could take an n by n box, and you could say, I will consider the set of all the minimal spanning trees of this n by n box, and I pick one uniformly at random. This will also give you a random spanning tree of your n by n box. And for this model, it is known that it has a nice scaling limit as the size of the box goes to infinity. And the scaling limit is described by the so-called SLE8 processes, the Schramm-Loebner evolution processes that we've seen also in Scott's talk. And this is of parameter kappa equals 8. So this was a result by Schramm, Loehler, and Loehler, Schramm, and Werner. And another result of scaling limit, which is different from the KPZ context or the quantum gravity context, is about critical percolation in the plane. So here in 2001, Smirnov proved that if you take critical side percolation on the triangular lattice, so not on Z2, it's not yet proved, then in some sense it converges to a conformal invariant scaling limit as the net goes to 0. And this striking result from 2001, this will be something very important later on in this talk. Okay, so the reason why it's very hard to study the scaling limit of things like a traveling salesman problem is because there is no polynomial or no easy algorithm known to compute what the best cycle is given the input, given the randomness. But in the case of the minimal spanning tree, there are many efficient and nice greedy algorithms. So for example, if you're given this this set of endpoints in the plane, and you want to schedule your visit of Buenos Aires, what you do is you take your map in advance, and among all the Euclidean edges that you have here, among all pair of vertices, you take the edge of minimal Euclidean length. So this would be this one. And now that you found this one, you take the second smallest edge, which would be this one, and you keep going until at some point you will want to create a cycle. And you are looking for a minimal spanning tree, so you don't really like cycles. So what you do is the first time you see a cycle, you just don't pick this edge, and you keep going. So maybe then you you take some other edges, and in the end, you stop the first time you get a connected graph, and by definition you get a tree because you didn't create any cycles. And it's not very hard to prove that this tree needs to be the minimal spanning tree. Okay, so removing all the cycles you found, you get the answer for your problem. Is this clear? So let me, if this wasn't clear, let me do it in the graph setting quickly. So now we have a random weights on my edges, and I will do it this side for you. So I want to find the minimal spanning tree in this graph setting. So what I do is I pick the minimal, I take the edge of minimal weight, I take the second smallest, and so on, until I will find a cycle, my first cycle, which maybe would be here, and I don't want to take this edge, and I continue until I connect the whole graph, and this gives me the minimal spanning tree of this n by n curve. So this algorithm where I kind of raise the level and I pick edges one at a time and in such a way that I don't create cycles will be crucial in this the rest of this talk. And I want to convince you that it's very much related to the model of percolation. So I'm sorry, the picture is maybe not. Do you see anything? Or? Okay, so okay, it will be hard to draw the simulation on the board, but what it's supposed to represent is then a Z2 graph. And in this model, each edge is kept with a probability p and is removed with quantity y minus p independently of the other edges. And what this first picture is supposed to represent is that when p is small, in the plane we see small clusters that are everywhere in the plane but are very small. And as p grows, you get more and more edges. And in these simulations, they are done in such a way that if p prime is bigger than p, the omega p prime configuration is above the omega p1. So they sit on top of each other. So I'm sorry that you cannot see much. And this way of putting all these different measures of percolation on top of each other is something very well known in percolation, and it's called a monotone coupling. And a standard way to define all these different configurations simultaneously together is to proceed as follows. You put uniform random variables on each edge of your graph that are independent, and for any value p, what you do is edge by edge, if the value is less than p, you keep the edge, and otherwise you remove it. And that's very simple, and it gives you a monotone coupling. And what you may already notice is that the randomness that one uses for this monotone coupling is the same randomness that I used for the minimal spanning tree. And if you didn't choose uniform random variable in 0, 1, then some other density random variable, you could still do this monotone coupling by adjusting the values. Okay? So I will rely a lot on this monotone coupling. And let me say a last word about percolation, for those who don't know. So it's a very important model in statistical fields for two reasons. The first one is that it's extremely simple to define or to draw, it's just this. And the second is that even though it's so simple to define, it has very nice behavior. There is a critical point that depends on the dimension and on the lattice. And below the critical point, as Eyal said, the belief is that clusters are very tiny, and it's much more than a belief now. So below the critical point, things are of logarithmic size. If you want to take a scaling limit, you won't see anything left. Above this critical point, the infinite cluster is going everywhere, and only tiny islands are remaining. And at the critical point, you get amazing things. You get fractal type of clusters, and if the lattice is the triangular lattice, it's even known that there is a very precise description of how these clusters look, and it's known that the picture is conformally parent, and a lot of things are known thanks to Smirnov's theorem. Okay, so now I want to convince you that percolation and monotone couplings of percolation will be very helpful for us in order to understand the macroscopic geometry of the minimal spanning tree. So let me repeat on a large scale what the algorithm that is called Christophe algorithm is doing. So imagine this is a larger portion of Z2, and I have my random weights. So we don't see, but there is a grid here. I'm sorry. So we have the random weights on these edges, and we start the algorithm. So maybe the first edge will be there, and then we keep going. And what I want to argue is that this algorithm, where we pick edges one at a time, one can parameterize this algorithm by the value of the edges that I catch one at a time. Namely, I can start at p equals 0 and raise the value of p, and take new edges whose label is equal to p, and raise p. And say p is less than the critical point. At that point, what did I do? I took all the edges whose value is less than p, and I know that it is subcritical. So the clusters of this percolation configuration are tiny. And what I've discovered is so the picture is a bit schematic, but what I discovered are sub-clusters of this percolation. Why? Because maybe in this cluster here, maybe I had some cycles and I don't want cycles. So what really is in the minimal spanning tree is something that is equal or less than this P cluster. Okay? And the whole point is that if I want to understand the macroscopic geometry of my minimal spanning tree in this box, for example, I want to know what is the path from this point to this point. Then in this Christophe algorithm at this level P, I have no clue how to go from there to there. I have only tiny portions of my minimal spanning tree. So as far as I didn't touch yet the critical point, the macroscopic geometry is still completely unclear. I only have kind of little dust everywhere, but there is no macroscopic branches. So the whole technology that I will explain to you later will be to try to say that all the macroscopic geometry of this tree will arise very close to the critical point. And this is why I will introduce a model later of near-critical geometry. So again, we don't see anything, but this was Christophe algorithm on the large scale. And so what I will try to prove in this, or give you an idea of proof in this talk is we will prove a scaling limit for the minimal spanning tree on a lattice for which we have Smirnov's theorem. Otherwise, even the critical percolation is not known to converge as the mesh of the lattice goes to 0. So this will be a minimal spanning tree on the triangular lattice. And to prove that there is a scaling limit, we will have to understand in this Christophe algorithm or in this monotone percolation how the tiny clusters do merge together around this critical point here. So maybe I should do a picture so the simulation was invisible. So when n is very large and we're almost at the scaling limit, maybe my p clusters are like that. And the only thing I know about my tree is things that are included in these things. But very close to the critical point, suddenly everything will kind of coalesce together and we will see big structures emerging. So that's what we will want to understand. So we will want to understand the geometry around this phase transition. So let me give you 3 references. The first work on this program that we've done was about building kind of geometric local time measures on the clusters of percolation and on the intersections of these. The second work was building a net critical scaling limit that I will define in 2 seconds. And the last work, last September, was about extracting a tree out of this net critical coupling and proving a scaling limit result. Okay, so let me tell you a little bit what I mean in general about net critical geometry. Let's take the easing model that was defined by Eyal 2 days ago. So in this easing model, if you are at the critical point, it's known by the work of Shelkak and Smirnov that the interface that you can imagine here converges as the size of your box goes to infinity to another SAE process, another Schwarzschild evolution, this time of parameter 3. So this picture is very nice. It's conformally invariant. We know how to study these curves and so on. If you go a little bit off the critical point, then you start seeing some supercritical behavior. But if you're not yet too far from the critical point, you still have fractal behavior there. You don't expect an SLE, well, in fact, in this case, it would be absolutely continuous, but it's not exactly an SLE. And the point I want to make is that there are much less symmetries when you move away from the critical point than when you are exactly at the critical point. Here you have all the conformal group that preserves the row. Well, here it's not conformally invariant anymore, so you have it's less rigid a priori, and it's harder to guess what the limits are. Before I tell you about planar percolation, let me give you another example of near critical percolation in the mean field case. So here we consider the percolation model on the complete graph, which is known as the Erdős-Reiny random graph. And it's well known that the phase transition here happens at p equals 1 over n. Namely, below that point, things are tiny, a little bit like in the plane. And above, you start getting macroscopic cluster, and everything happens at this 1 over n. But now, if you want to study the coalescence process of cluster that create these macroscopic ones and go to a giant scope component, you need to rescale your process around the critical point at the right speed. And this is exactly what we will need to do in the plane. You need to rescale your parameter p at the proper speed. And what we will do in the rest of this talk is we will change our parameter. P will be too abrupt, too fast. Things go too quickly from nothing to the full picture. So we will change our parameter and we will call it lambda, but we need to tune to find the right zooming around the critical point. And I will explain quickly why we do this in the complete graph and what we need to do on the plane. Okay, so let me give you a quotation by Allen and Spencer. So imagine you want to understand this phase transition on the complete graph. You take n very large, or even n going to infinity, and you want to see how the small clusters merge together to create a giant one. And what they said is, with lambda equals minus 1 million, we have, say, a feudalism. Things are very tiny, you have small division. Many components are each vying to be the largest, and as lambda increases, the components increase in size, and a few large components emerge. An already large friend, I didn't make the quotation, has not the chance of becoming larger than a smaller Andorra. This I didn't make it either. And so on and so on. So, until the Roman Empire has emerged. So in some sense, in this talk, the main tool will be to match this quotation, but not in the mean field case, in the planar case. So we'll have to understand how to go from feudalism to Roman Empire, but where villages are in the plane, not in the midfield. And since the talk is about minimal spanning tree, let me mention this result of last year of the chairman Christina Goldschmidt and Adario Berry, Broutin and Mirmont, where they consider the model of minimal spanning tree on the complete graph. So they have random weights and edges of the complete graph. And they prove a scaling limit result as the number of vertices goes to infinity. They get a limiting tree. And in some sense, they extract this tree out of this, not out of this quotation, out of the theorem, the tree also proved the year before. And in some sense, what we do is the same type of results. We seek for a scaling limit, but we are in the plane. And that will make the technology different and also the topology of convergence different. Okay, so let me try to describe feudalism towards the Roman Empire in the plane. So I take this monotone coupling of percolation on the triangular lattice. And what I want to argue is that if I do this monotone coupling, so imagine you have, to define it, imagine you have ID uniform random variables on each hexagon, and you raise the level P. What we want is a scaling limit result. So we want to let the mesh go to 0 and to find something at the scaling limit. If you look at your monotone coupling and you just rescale the lattice and you don't do anything else, it will be like the previous picture I had before. You will see nothing there. It will be completely blue here. And there you will have some nice quadratic pictures. So this is not good. You need to do an additional step. Not only the lattice mesh needs to shrink to 0, but also you need to zoom at the right speed around the critical point. So as in the complete graph setting, we need to change the parameter from p to some lambda by zooming around the critical point. So how do we do? So we change the parameter, and we need to find the value of the zooming arita. And if arita is chosen too small, if you zoom too fast around the critical point, well, basically at large scales, the process is not going to move. Maybe tiny things will happen, but at the same limit, you will see just an identical picture as a process of lambda, but this is not good. If arita is too big, if you didn't zoom fast enough, well, the same behavior as before is happening. It's not good either. So you need to find the right tuning. And the right tuning is given to us by a deep theorem of Keston in 1987, where he found what the right tuning was in terms of arms exponent in critical percolation that I will not need to introduce. Okay, so let me very roughly tell you where this scaling comes from. We have two different scalings, one in n to the minus 4 thirds in the mean field case, and a different type of scaling in the plane. So in the complete graph case, it is known that the clusters at the critical point p equals 1 over n are of size n to the 2 thirds. And it's even known what their geometry is, but it's not needed for this proof here. But their geometry, they are basically Albus random trees with order of 1 cycles. And you are at 1 over n, say, you want to raise a little bit the value of p in such a way that things are non-trivial but non-degenerate. So if you do that, you don't have many large clusters, and between two clusters of volume n to the 2 thirds, you're on the complete graph, so you have n to the 2 thirds squared edges going from one to the other. So it makes sense that you need to raise the value of p by 1 over the number of edges going from one macroscopic cluster to another. And this gives this n to the minus 4 thirds. In the plane, what's going on is, say you have a window of size 1 and your mesh is very small. You also have finitely many large clusters, as in the complete graph. But now the big difference with the mean field setting is that the number of points or edges or hexagon going from one big cluster to another, it's not anymore the volume of the first one times the volume of the other one, because you're in the plane, and it's only the frontier that will matter. And the number of points lying between two large clusters, these are the pivotal points. And we now know the critical exponent of these, and we can compute how many pivotal points you have between two large clusters. And once you know that, it explains well on the heuristics level why you need to tune at that. to make a proof out of that is much harder, and this is the content of test and see. So is that part clear? Okay, so so now that we have the right tuning, I can define what I mean by near critical percolation. I scale space, and I zoom around the critical point at a speed that I know will make things non-degenerate. And I want to ask, is there a scaling limit as the mesh goes to 0? And what I'm looking for is a kind of a cut-back process at the scaling limit that will be the critical slice at lambda equals 0 and will be something non-trivial for other values of lambda. And when you look for such type of scaling limits, of course you need to find a setup, you need to find a topology, and in probability one seeks for some kind of Polish space for which the points of this Polish space are naturally related to percolation configurations. So if you were to prove this, I guess the first setup you would try would be the following. After all, a critical percolation is just a random coloring of your plane. You have small hexagons that are black with 0.1 small hexagons that are white with 0.1 So it's easy to encode this critical percolation using a distribution in the plane that tells you if this little hexagon is black or white. And you all know that this distribution in the plane converges in the appropriate setup to a Gaussian white noise in the plane. So you might think, okay, the scaling limit of critical percolation is just given by Gaussian white noise in the plane. But there is a very deep theorem of Benjamin Icala and Schramm in 1999, where they say that there is no way to find any percolation in Gaussian white noise. In some sense, the continuum percolation and the Gaussian white noise, they live in orthogonal spaces. That's a bit the setup that they discussed. And on an intuitive level, the reason is that if this is at a very large scale, you can change just one hexagon in the middle, which will have a drastic effect on percolation, but which will be almost invisible in any setup you take to take scanning limits of white noise. So it's clear that things are much more sensitive, and that's a bit the idea that they have. So Sobolev spaces or things like that are not the right tool to pass through the limits, and therefore you need a bit of imagination, and several setups have been invented in the past, which started with Eisenman and Eisenman-Burchard, and then Kamiya and Newman. And the last setup is the one by Schramm and Smirnov of 2001. And that's the setup I will use. I will not tell you much about this setup. I won't need the details of this space so much. But in a few words, the idea is to encode the percolation as follows. For each quad or each tube like that in the plane with two prescribed arcs, what you want to know is whether your percolation crosses from left to right or not. And put it this way, it seems natural to say that the space of Schramm-Smirnov will be just 0, 1, yes or no, to the power, the number of the whole family of quads that you can embed in the plane. So that's one possibility, but that makes your space not separable and a bit nasty to work with. So what they do is they select a subspace which is much smaller and which in some sense preserves a monotonicity that is induced from percolation. So I will not go into more details, but they find a topology on this space that makes the space compact, Hausdorff, and nice, and which is very suitable to the scanning limit. So I will call this the Schramm-Smirnov space. And let me first analyze what's going on at the critical point, which corresponds to lambda equals 0. For any mesh eta, critical percolation gives you a measure, p eta, which is the measure on this Schramm-Smirnov space of percolation H, and endowed with some distance that is non-explicit. And what you might ask is there a weak limit for these measures beta, and is there a unique such limit? And there is a theorem which tells you that indeed there is a limiting measure, a continuum percolation, which is this p infinite, and this measure is unique. And by far, the main ingredient is the striking result of Smirnov in 2001, the Cardis formula, in any fixed domain. But you need a little bit more to prove this result because you need the joint law of all the crossings. And a joint Cardis formula even with two crossing in the plane. This is not something that is easy to prove. So you need some extra arguments to get the full scaling limit. And this was done essentially by Camille and Newman in 2006. And what we've done for lambda equals 0 is basically nothing, just putting things together, but there is nothing deep there. So this handles the case of the critical size, and what we want to address is what's going on away from this critical size lambda equals 0. So let me repeat the question that I had before. Let's take, for example, lambda positive. Let's renormalize at the right tuning around the critical point. Is it the case that the measure induced by this slightly near critical percolation on the space of Francine, does this measure as a limiting object when the mesh goes to 0? So here's the answer. So what we proved that indeed there is a unique such limit. The fact that you have subsequential scaling limit is obvious because the space that the design is compact, so tightness is completely obvious there. But the fact that there is a scaling limit is the hard part of the proof. And we also proved that the whole process, the Cadillac process, also has a scaling limit as the mesh goes to 0. So if you just want to think of tightness first, this is less obvious because you need to prove tightness in this sort of topology there. So we do obtain a scaling limit for an critical percolation. And let me draw a little bit how this looks. So if I want to take lambda negative, for example, and pass to the limit, what I will obtain in the plane is something with continuum clusters like that. And we are below the critical point, there is no infinite cluster, so this would be lambda negative. And if lambda is positive, what we see is an infinite cluster. But now the ions, the holes, they are non-degenerate. We have tiny ions like that. And what we can show is that there is a correlation length which depends on lambda. And the correlation length basically means that the size of the clusters you see is of order lambda to the power minus 4/3. So as lambda goes to 0, you get something which is more and more scale invariant. And let me give you another result that is due to Donna and Werner a few years ago. What they had at the time, they did not have a scaling limit, but what they proved is that for any subsequential scaling limit, and therefore now for the process we have, if you look at the boundary of this near critical picture, these boundaries, they are singular with respect to FLC. So, namely, there is no hope to try to define these near critical couplings just by simple Radon-Nikodym derivative with respect to the critical size. So their result shows that the object we obtain is something that is non-trivial. It's still fractal looking, but it's not at all FLC. Okay, so now I want to tell you a little bit about how the proof works. If you just wanted to prove the lambda equals 0 case, which was sort of known, as I mentioned, the tightness is obvious. The space, the underlying space is compact. So the real difficulty is to prove that there is a unique object at the scaling limit. And the main ingredient for that is Cardis formula. So once you have this example of lambda equals 0, a natural guess to go to lambda non-equal to 0 is to follow what Smirnov did in the critical case. Namely, it would be nice to find an observable that will be massive harmonic, it won't be harmonic anymore, and which will allow you to pass the limit and have a massive model at the scaling limit. The problem is that even at the critical point, the observable of Smirnov was not exactly harmonic, it was only approximately harmonic. So we don't expect the existence of a massive harmonic observable that is exactly massive harmonic. So that's the first issue. And the second one is that a posteriori, you know that the mass should scale as this power of P minus Pc. And it seems very non-trivial to analyze, to get a proof using such massive observations. So this is not what we did. And instead we relied on a perturbative approach that I will explain here. So the idea is that we start with this object that is basically the scaling limit of a critical percolation in this space of Schramm-Einstein. And this is our critical slice, and what we want to do is we want to go away from the critical slice. We want to add infinitesimal mass to these pictures, or to remove infinitesimal mass. And here, an important point is that you are at the scaling limit, so you do not have hexagons anymore. They are not there, you just have some continuum. So you cannot say that I pick some hexagons and I turn them from white to black. This you cannot do anymore. So you need to select some places in your picture to add a little bit of mass. And a natural idea is that there are some very specific points in this picture, the pivotal points, and you will want to add a little bit of mass to this pivotal point to make your picture a bit more simple. And the first difficulty here that I will not go into is that you would need these pivotal points to be measurable in the space of Schramm-Einstein, and this is actually not so. This is a very technical part of the book. But assume you can localize where these points are in this Schramm-Einstein sense. What you would want to construct is a mass measure on these pivotal points, and then you will use a Poisson point process whose measure will be this mass measure at the critical point times the Lebesgue measure on the lambda line. And equipped with this additional randomness, so that's the critical slice, and the additional randomness would be given by this Poisson point process. Potentially, what you can do is, as lambda increases, you can collect which pivotal points have switched from black to white, and you can follow what this means geometrically, and this will make your percolation heavier. So this is the strategy, but it's naive in several respects. The one we struggle most about, I won't tell you, about topological issues that arise from the Schramm-Einstein space. In some sense, you need to pay for the fact that things are compact a little bit. And two issues that are easy to grasp are the following one. If you follow the strategy I gave, it turns out that you have too many pivotal points. Namely, the mass measure that you would want to build will be locally infinite everywhere. So it's not so convenient when you want to do a Poisson point process. So what you need to do is you need to regularize. Basically, as in all the talks we've seen, in Martin's talk, or in Scott Sheffield, or in many talks, we need to remove a little bit of the singularity. And in this geometric context, what we do is we remove all the points that are pivotal up to a distance less than epsilon. We keep only the points that are pivotal far. And if you do this, then we can prove that we can define a mass measure on this point that pass to the limit a little bit, like if you had a random walk in d equals 1, and attached to this random walk, you look at the normalized measure on the zeros of this random walk, and this gives you a coupling random walk with this mass measure. And you know that it converges to the coupling of a Brownian motion equipped with its local time that is measurable with respect to that. So what we need to do here is the same thing, but in this percolation setting. And the proof of this is a bit difficult for one essential reason, that there is no strong Markov property. And even though the underlying measure is ID measure, you do have long-range dependencies to build these measures. So that was our first work on this subject, with motivation to go to the technical study. So the second difficulty is a consequence of the first one. We introduce the cutoff, so we need to analyze what might be the effect of this cutoff. And namely, when you start with the critical picture and you raise a little bit the level, it could be that very small clusters will have a big impact on the global picture. And these small clusters, you neglected them when you introduced your cutoff. So you want to prove that such scenarios and multi-scale scenarios like that do not arise when you use cutoff. And this is the second result we proved. And with some additional difficulties that I'm not speaking about, you can get the scaling limit result I discussed before. So now I want to give you some properties of of the process. And the first property that I want to give is the following, that there is a scale invariance of this inner critical picture. And I want to illustrate it by stealing a slide from Martin's talk. I think the slide was like that. There was a universality point here that was Gaussian in some ways, and many models were supposed to converge to it. And here one of the directions could be critical percolation of the triangular lattice. And this we know it converges to continuum percolation. But there are many other things that should converge to this. For example, Z2, critical Z2 percolation should converge to that point as well. But it's not known. So in some sense, as in Ivan's talk, we are at the Moivre-Laplace scale also, percolation. Okay, and now to match with Martin's talk, one can imagine a direction like that. Why? Because if you take something slightly supercritical and you do what physicists like to do, namely a renormalization group analysis, so you kind of look at percolation on eta Z2 and then eta over 2Z2 and kind of renormalizing more and more, supercritical would diverge to a point at infinity here, which is not as interesting as in Martin's talk. This was very interesting there. Here it would be very boring. It would be a supercritical percolation at the scaling limit, so something which is degenerate. So what we built in this work is it's kind of the line that is there, that is stable under this renormalization group. So we have a kind of eigenvector of this renormalization group process, whose eigenvalues is this 2 to the 3/4. So in some sense, this work starts building a little bit what the picture of a renormalization group should be for percolation. We get this unstable manifold here. Okay, so how much?
0.
Oh, 0. So 0. So let me skip. Can I take 1 minute?
Please.
So very quickly we obtain other scaling limits of processes like invasion or gradient percolation. And this gives us Markov processes on this Schramm-Sumner space, but they are non-Taylor processes. So that illustrates a little bit that things are a bit nasty there. We get the scaling limit for the minimal spiral tree. I don't tell you about the proof. We get some properties for the Hausdorff dimension of branches and some geometry things. And let me just tell you open problems and I will be done. So the first open problem that I like is that we can prove that the scaling limit of the minimal spanning tree is rotationally invariant, which is not obvious because the triangular lattice obviously is not rotationally invariant. So that's a nice consequence, but what is expected is that it is not conformally invariant. And it's not so easy to design a statistical physics model on Z2 that is scaling invariant and rotation invariant at the scaling limit, but is not conformally invariant, and we do not manage to prove this here. Another open problem is to find the exact order of dimension of the branches, and even in the physics literature we don't know what the number is, so it's a little bit frightening. And the last open question is that I mentioned at the very beginning the scaling limit of the uniform, not the minimal, the uniform spanning tree, and it's known to be SL8, and we don't even know how to prove that they are different. We do expect very much because we expect they are not conforming now, but we don't know how to prove this. And this picture shows, well, you don't see much. To show a minimal versus a uniform one, and they look very much different. So thank you for your